In the previous parts of this lesson, we reviewed a whole bunch of formula for the perimeter and the area of a whole bunch of different shapes, right? So in this part of the lesson, we're going to see how those formula, specifically the area formulae, relate to each other as an axiomatic system. Geometry is an axiomatic system. And you might be going, well, I've never heard this before. What does axiomatic even mean? It simply means that we accept a handful of simple ideas as true. We don't have to prove them. You sometimes look at them and you go, oh, that's just obviously true. Nobody has to prove that to me. And we call those ideas axioms. Or sometimes a more modern term for that is a postulate. Axioms and postulates mean the same thing. Okay, so we accept these axioms as true. Nobody has to prove them to us, but then we use those axioms to derive other more complicated ideas from those axioms. Let me give you an example of an axiom that you probably heard about in another math class. All right, it goes something like this. And it has to do with, say, points and lines and stuff like that. So we will call this an example of an axiom. Something that's just obviously true. So what I'm going to do is I'm going to take and draw 2 points, and maybe I label them. I name them A and B. And then I ask, okay, so through these 2 points, how many lines can I draw? And so I think about it for a second, and it only really takes me about a second. And then I go, you know what? There's only one line that I can draw through those 2 points, right? That's just, it seems obviously true. There's only one line that goes through those points. And this is an example of an axiom, something that is just sort of self-evident, right? If I have 2 points, I can only draw one line through those 2 particular points, and I might write this axiom something like this. Through any 2 points, there is exactly one line. And sometimes it's stated like that, and sometimes it's stated any 2 points determine a line or something like that. So this was a pretty old example of an axiom, and it's something that I think is so obvious that nobody would have to even prove it to you or even tell it to you. You just think about it for a second, oh yeah, that makes sense. There's only one line through any 2 points. Okay, so we're going to try to demonstrate this idea of an axiomatic system with the area formulae specifically. Okay, so let's kind of recap here which formulae we are talking about. So area as an axiomatic system. And so what shapes do we have? Well, let's see, we talked about a square, of course. Look at this beautiful square. And we said that was side squared. And then we have ourselves a rectangle. And its area was a base times height. And then we had, I believe, look at this is perfect parallelogram. Okay, and it was also base times height. We throw in like a little height in there that makes a right angle. Got a triangle. A triangle, which was base times height divided by 2. Again, you must have had some sort of height in there. And how about a trapezoid? I think we covered this one. Trapezoid, which was a half base 1 plus base 2, or at least the sum of those things, multiplied times the height. Needed a height in there. Yeah. And then the last one here was a let me try that again. Was a circle. Boop. Perfect. And it was pi r squared. So the question that we're asking ourselves right now is, like, of these 6 shapes and these 6 different formula, which of them should we accept as true? Which one should be the axiom? Which one do you think that we could use to derive all of the other 5 from? Which one is the simplest one? And the answer to that question is the square. So we're going to demonstrate how we can use the square to come up basically with the other area formula. We accept this one as the axiom or postulate. A is equal to S squared. Nobody's going to have to prove that one. We're just going to go, okay, I'm fine with that. And then show how that can help us come up with something like the area formula for a rectangle, a parallelogram, and so on.